So the topic of our conversation today is going to be how can we prove that systems obtained by interconnecting components are going to have desired properties? And we are going to be using this tool of assumed guarantee contracts. And of course, the reason we are interested in such a question is because today we have problems, right? The frequent news of recalls and recertifications in the systems industries, particularly in automotive and aerospace, is an eloquent testimony to how hard it is to build systems. And we can ask the question, okay, why is that so? And there are many voices from both industry, academia, and also from government agencies that tell us that today we lack theoretical and practical frameworks to prove that the systems obtained by interconnecting parts, okay, will have desired properties. So as a reflection of that, for example, we can see that in the systems industries, particularly in aerospace, people talk a lot about the concept of digital engineering. And this is the definition of digital engineering from the person who heads digital engineering for the entire NASA. So Terry Hill says that digital engineering is all about, okay, making products faster with better budgets, better specifications. How? Through the integration of processes, tools, techniques, along with a seamless flow of information. So we notice that this need for integration is at the core of what is being expressed here. Okay, so similarly, if we look for voices coming from academia, Joseph Sifakis a few years ago told us that the time is ripe for us to develop the technical advancements to contribute towards a science of design. And then he talks about how this vision is both intellectually challenging and culturally enlightening, and it is at least of equal importance as the quest for scientific discovery in natural sciences. So very imposing words, calling us to develop a science of integration and of engineering design. So as we think about the kinds of requirements that we should impose on any theoretical and practical framework to do system level design, we can think about it needing to address a few requirements. So to start with is that in complex systems, we are going to have at the table people representing multiple concerns. So we are going to have people from manufacturing and financials, from safety and security, from legal and certification. And whatever theoretical framework we use, should better allow us to both express and manipulate the concerns that all these various stakeholders are going to bring to the project. The second aspect that we would like to address is the fact that today in industry, system integrators and suppliers enter into business relationships through this concept of a legal contract, whereby they are bound in a business relationship. And sometimes we tend to have frictions in our supply chains. So we can dream about a situation in which these parties, in addition to exchanging this legal object, they will also exchange a technical object, that we can call a technical contract, whereby the integrator would know a priori that if the supplier implements this contract correctly, this implementation is going to play well in the system and the system will have desired properties. The next challenge that we can think of when brainstorming about requirements for a theory of system design is the fact that today for complex systems we use heterogeneous forms of analysis to address the various pieces of the cake. So we are going to be using finite elements to address anything having to do with structures and thermals. We will use circuit theory to handle energy transfers. We use label transition systems and our software tools in order to analyze all our code in the system. And the question becomes, well, after we have analyzed all these pieces in isolation, how do we stitch all that data together in order to reach conclusions for the entire system? So since the early 2000s or so, building on the tradition that came from computer science, from control systems, from systems engineering, and a few other areas, the notion of using assumed guarantee contracts to do system level design was proposed. And the idea here is that contracts are going to give us two things. So contracts give us both mathematics, but they also give us a methodology in order to address key tasks of complex system design. The first one has to do with what we can call system integration. By system integration, we understand the generation of a system by interconnecting existing parts. So we have multiple providers and we are generating a system out of those parts coming from the multiple providers. Contracts will give us an operation that we call composition. We are going to be illustrating this soon. And this operation of composition will generate the specification of the whole from the specification of the parts. Contracts can also allow us to do the opposite. We can say the opposite being that suppose instead of going from the parts to the whole, we want to do the opposite. So suppose that you know what is the specification that you want your system to achieve. And you also know the specification of a piece of your system. Say, for example, you're developing a car and you know what a car has to do, and you already develop an engine and you have a contract for your engine. So there is an operation called quotient that allows you to fill the whole of your system and to say, what is the specification of what I need to add so that my system does what I want it to do? So this is what we mean by this task of system integration, okay? Understanding the whole by my data from the parts. Contracts also have something to say about an orthogonal task in system design, which we refer to as handling multiple viewpoints. So the story here is as follows. Sometimes it can happen that at the same organization, there are multiple groups of people who work on the same object. So one group may be in charge of generating a functionality specification. Another group may be in charge of developing a power or timing or you name it, specification. So what we want to do is to bring all these aspects together into the same contract. And we are going to have an algebraic operation called merging that allows us to summarize all this data from the component. Okay, so let's just keep in mind that contracts give us these two things. Okay, so they give us methodology and mathematics to do system level design. Okay, throughout our conversation today, we are going to refer a couple of times to a tool by the name of Pacti. So Pacti is a Python package that we have been developing for the last couple of years that is used in order to apply contract-based design to address applications. And we have some applications of Pacti, both to cyber-physical systems, which we see on the left-hand side of this slide, and to synthetic biology, which we see on the right-hand side. So on the cyber-physical systems end, so we have done applications to space mission design in collaboration with NASA's Jet Propulsion Laboratory in the Pasadena. And other applications are in multi-agent robotics and in self-driving cars. And regarding our applications to genetic circuits, I should say to synthetic biology, we have applications to genetic circuits, both in bacteria and in mammalian cells. And typically, the main problem that we addressed is the fact that when we develop genetic circuits, it's very common that the behavior that a component displays when it acts in isolation is different from the one that it displays when it operates in conjunction with other parts of the system. So contracts ended up being helpful in order to characterize contexts of operation of all the circuits. So that being said, what we have ahead of us in this set of slides is the following set of topics. So in order to brainstorm why might we need different forms of analysis than one we use today in order to address complex systems. Okay, we are going to consider first a case study developed by NASA's JPL. Then, and this is going to allow us to introduce some of our language of contracts and to consider some other algebraic operations. Then we're going to consider a case study in self-driving cars that will introduce additional operations on contracts. In point 3, we will look at the question, okay, but what are the actual mathematics that we are using? And then, time permitting, we have points 4 and 5 that are applications to control systems and to compositional security in cyber-physical systems. So let us begin by discussing this case study that JPL implemented. So the situation that we want to address is as follows. Suppose that we are developing a spacecraft to satisfy a particular rendezvous mission. So this means that we are developing a spacecraft that is going to leave Earth and it's going to go meet some object of scientific interest, such as an asteroid. It's going to make observations of that object and it will report them back to Earth. So JPL is understanding a spacecraft as an object which at any given point in time is doing 1 out of 4 possible tasks. Okay, so the tasks are represented by these red squares and rectangles that we see on the slide. So when the spacecraft is in DSN mode, that stands for Deep Space Network. This is the communication infrastructure that NASA uses to talk to spacecraft. So that means that, okay, if we are the spacecraft and we are in DSN mode, okay, we are going to point towards Earth and we are going to exchange data with Earth. The spacecraft being in SBO mode means small body object. That means that the spacecraft is going to align itself towards the object that it is meant to study, and it is going to deploy its scientific instruments in order to gather data. TCM stands for trajectory correction maneuver. That means that the spacecraft is going to engage its thrusters in order to approach the object that it is supposed to study. And charging means, okay, look at the sun and receive maximum energy from the sun. So this is how we understand the operation of the spacecraft. And there are two high-level questions that we want to address about a given spacecraft. So the problem setting looks like this. Suppose that we have a given sequence of these modes of operation. So somebody gives you a string that says, okay, first you're going to do communication with Earth, then you change trajectory, then you charge, then you blah, blah, blah. Okay, and we have a string of these modes of operation. We want to answer two questions. The first is it possible to carry out this sequence of tasks, with our energy level, with our charge level at the battery never falling below a certain threshold? So we do not wish to lose access to our object, in space. And the second question is, can we make sure that this spacecraft will be able to both record and transmit all the goals set by our science teams? Okay, so two high-level questions. So the first about power, the second is, can we gather the data that we need to gather from our object? So at this point in the design process, if we were working for NASA, so we would be looking at something called the Systems Engineering Handbook in order to move forward in the design process. And this handbook tells us what is the flow of design steps that we follow in order to do a spacecraft. And at this point in the design process, of course, we are in the extremely early stages of design. Okay, what we have are high-level mission objectives. What is going to happen next, according to this diagram, is we are going to engage in conversations with the multiple stakeholders of the mission, and our high-level requirements are going to be eventually refined into low-level requirements that we can assign to the parts, and then we can actually produce our spacecraft. So the problem that sometimes we run into when following these design processes is that feedback loops can be very deep, in the sense that decisions are made very early on in the design process. Then we start developing simulation models and we carry out analysis, and we figure out, deep in the process that there are some problems, and then we go back and reconsider what we are actually doing. So the question that we wanted to ask here was, is there a way of implementing a much shallower feedback loop in the mission in such a way that we can get, quick feedback about the feasibility of various spacecraft configurations, before we commit, to pursuing analysis on one of them? And the high-level requirement that we are imposing on our analysis is that we do not want to use simulation models. Now, remember that simulation models are really the workhorse of engineering design. We simulate everything. But the reason we do not want to use simulation models at this stage in the design is actually, there are at least three reasons. The first is that we are so early in the design process that simulation models may not just be available at all. They haven't been developed. The second is that detailed simulation models of our components, by definition, are able to be used by about 3 people in our organization. Right? So these are the people that have deep expertise in that particular subject. So we can forget about putting a simulation for the entire system that knows everything about thermals and electricals and electromagnetism and communications and all of that, right? What we would like to have is an analysis tool that the systems engineer that is looking at the entire system can actually use in order to understand trade-offs between parts. And the third point is that even if simulation models were available, these are objects that usually take a significant amount of hardware and software setup before they can be used, and they generate insight only into specific runs of the system that we have to carefully choose. Okay, what we want to do at this stage is to understand entire sets of trajectories, and as you can imagine, in order to carry out this early analysis, we are going to be using these contracts that we have been discussing. So now we are going to define what these objects are, before we apply them in this mission. So we are going to be representing components and systems using this notion of assumed guarantee contracts. So what are contracts? Contracts are formal specifications. So the word formal in that expression means mathematically understandable specifications that come in two pieces. A contract is going to tell us what the component does. So what the component does is going to be, what I can expect this component to give us, okay, in the system. But the contract is also going to tell us what are the expectations that such an object makes on its context of operation in order for it to be able to deliver its guarantees, okay? So notice that what a contract is the mathematical analog of a component datasheet used in engineering. A component datasheet in engineering always tells you your component is going to do blah, 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 but you have to respect certain requirements in order to use this component. You have to give it the right voltages and you have to operate under the right temperatures and so on. So this notion of a contract is exactly the object that we already use in engineering design in order to do compositional system design. Okay? So we are simply mathematizing that notion. So to make things more concrete, on the right side of the slide, we see that a contract is really understood as a pair of assumptions, guarantees. So for example, if we were developing a security application, this is a perfectly valid contract. So we can say, I am going to guarantee that my car is able to make it to its destination with a probability of at least 1 minus epsilon, under the assumption that at most 30% of my location sensors are under attack. So this will be a good or a valid security specification to attach to a self-driving car. So the thing about contracts is that they are useful not only because they allow us to express specifications, but because they have as a rich set of mathematical relations and operations that allow us to do analysis and design using such objects. And let us now introduce some of this. So to start with, contracts have a notion of order. So we know when a contract is more refined or more demanding than a different contract. We'll talk about that more soon. And the second is because they have a certain number of binary operations that allow us to do analysis, as we just discussed. In this space mission case study, we are going to be using two operations on contracts. The first is what we call composition. So the idea with composition is that we understand a system as an interconnection of parts, as shown in the diagram on the bottom left of the slide. So here you can see that we have an interconnection of three boxes that represent components. The boxes have well-defined ports. So in this case, they are input and output. So the first guy has, input I and output input I1 and output O1. And every component also tells you its contract. So every component will tell you, I have assumptions, AI, and my guarantees are GI. So with composition, we can go from a diagram that looks like this to a diagram that places a box around the entire structure. So what we get to see are the top-level inputs to the system and the top-level outputs to the system. And this A parallel and G parallel are going to give us the specification of the system that we get by composing these two elements. So this is a key operation in system design, of course, going from the parts to the system in such a way that we abstract whatever is internal to the interconnections. So this is one operation. The second operation we'll use is what we call merging viewpoints. So the situation here is as follows. If we look at the diagram on the bottom right of the slide, so the outer box here represents not multiple components, but just one component. And the internal boxes represent different aspects of that component. So here we can understand A1 and G1 as the contract that speaks about the power aspects of my component. A2 and G2 is going to be the contract that represents the functionality or the timing or the security aspects of that component. Okay, and through this notion of merging, we go from these multiple viewpoints into a single contract that knows everything about my component. This operation is actually quite useful from the perspective of specification capture. When we are writing specifications for components, this notion of merging allows us to write the specification in pieces. And we know from our experience in software design that modularity is very helpful for engineers because we are less prone to errors when we are focusing exclusively on one thing. So just to make sure we are on the same page, let us consider a quick example about system composition. So let us consider the situation of two components connected in series as shown in this slide. So we have components M and M prime with those inputs and outputs. So component M has input I and output O, and M prime has input O and output O prime. We are going to assign contracts to each of these two components. So for component M, we are going to assign a contract that says if my input is bounded by 2, my output is going to be equal to my input. And for the second component, we are going to say, if my input is bounded by 1, my output is going to be equal to my input. Okay, so we have two components. We know their specifications. Notice that we do not know their implementations. I mean, we don't even know whether these are chemical elements or electrical or anything. All that we know is this contract specification attached to our components. So this is the question that we are trying to address. Imagine that we build such a system, and after building this system, we provide it to a third party for use. What specification would we tell that third party that our system obeys? Okay, so I'm going to repeat this because I want us to be on the same page regarding the question. So the question is this: we have this system, we implemented it. Now, we want to provide this to a third party, and this party is going to be a user of our system. So how should we tell that third party that they should use our resulting system? So this is what we mean by contract composition. What we know are the contracts for the parts, and we want a contract for the entire thing. If we reflect for a few seconds, I would about the specification of the entire system, okay, we would probably reach a contract that looks like this for the entire system. We would say, okay, what I would tell my user is that if they make my input less than 1, they can expect the top level output to be equal to the top level input, right? And I would like to point out a few virtues of this system level specification. The first virtue of this specification is the fact that it does not mention the internal variable O. Okay, notice that this is exclusively in terms of input I, output O prime, and top level input I. And the reason it doesn't mention the internal variable O is because our user doesn't care about that variable, right? Our user wants to place a box around this entire structure, and our user wants to see, just tell me, what do I need to do at the input, and what am I going to see at the top level output of my system? So this is virtue 1. Virtue 2 is the fact that assumptions are given only with respect to the top level inputs. And the third virtue is that guarantees are given only with respect to the top level inputs and the top level outputs. Okay. And a fourth thing that I would like to mention about this is the following. Why did we compute the fact that my top level input had to be less than 1? You could say, look, I could have made my input to be something less than 2, but if we had made it less than 2, notice that we could put a 2 in the first output of the output of the first component, and this value of O is outside the range of what the second component is expecting. Okay, so by making I to be less than 1, we make sure that the components M and M prime are going to be operating under their expected assumptions, which is the only way in which we can rely on them providing their guarantees. So this is the reason we have this I less than 1. So, if we use Pacti to approach this, we could have computed the same specification by using the tool in the following way. So if we look at the code on the right-hand side, lines 1 through 5 are instantiating our first component, the contract for the first component M. So you can see that we are specifying what are the input variables, the output variables. The assumptions are input less than 2. And you can see that we have the same guarantees. Lines 8 through 12 are instantiating our second contract. And in line 15, we are asking Pacti, give me the specification of the system obtained by connecting those two objects. And the output that we get from the tool in this case is what we expected, okay? We have top level input I, top level output O prime, and these assumptions and guarantees. So in this example, we saw how we can go from contracts of pieces to the contract of the entire system. Now, I would like to make a small variation of this example in order for us to see that composition can be used for a different purpose. So we just consider this example, and then let us make a small variation of this example. So same situation as before. We are interconnecting these two components, but we are going to change their contracts slightly. So the second contract, or the contract associated with C prime, is going to be the same as before. So we are going to have, my input is less than 1. I'm going to promise that the output is equal to the input. But for the first component, we are going to say, as long as my input is less than 2, I am going to promise that I will make my output to be bounded by 3. Okay, so this is all we know about the two components. Now let us imagine that we go through a similar exercise as before. We build such a system and we give it to a friend who is going to be a user of our system. What specification would we tell that person that is obeyed by our system? So we could go to Pacti as we did before. So in lines 1 through 5, we instantiate the first contract. In lines 8 through 12, we instantiate the second contract. In line 16, we are asking for the system level specification. And in this case, we have an error. And the error that the tool is reporting is the following. So Pacti is trying to generate a system level specification that does not say anything about the internal variable O. And remember that the reason we don't want to say anything about O, right, is because the user doesn't care. I mean, the user doesn't see the internals of the system. However, Pacti is using these contract relations that we're going to introduce soon, and is trying to get rid of O in a logically correct way by generating an abstraction of the contract. And in this case, the tool is saying, I am logically unable to get rid of this variable. And to me, it was remarkable that the fact that there is a logical impossibility to eliminate the internal variable O is related to the fact that in this system we have a potential bug. And the bug is that we are potentially sending 3 units to a component that is asking for a maximum of 1 unit. So if these were electronic components, we can be sending 3 volts to a component that is asking for 1 volt. When I talk to colleagues from industry, something that we discuss is the fact that this is not the kind of bug that we are guaranteed to catch in simulation. In simulation, it could have been the case that O happened to be equal to 0. So 0 passes this guarantee, and 0 also passes this assumption. So our simulation would have been successful. Of course, we may say, okay, but if I choose a large enough number of simulations, or if I think about my corner cases, I am going to catch that. And the answer is, of course. But if we have 10 components, 15 components, now we have to think about all possible corner cases, and the combinatorics are such that we get the point, right? The point is that by doing these operations directly on the contracts, here we are using the specification as an object of computation, and because of that, we are able to catch at once all possible errors. And if the specification that we get of the resulting system work, we have 100% guarantee that the system is going to obey that specification, provided, of course, that we have components that respect their local contracts. Okay. So having said that, having discussed these 2 operations on contracts, let us apply them to our case study on space mission design. So let us remember that what we wanted to do was to design a spacecraft that is going to follow this particular schedule of modes of operations. And there are 2 very high-level questions that we are addressing. Can we make sure that our charge remains above a threshold? And can we make sure that we gather all the data as set by the scientific mission objectives of our mission? So we said that we're going to be using contracts, and we proceed as follows. So this is how JPL proceeded. So as the spacecraft is evolving in its mission, so we are going to be keeping track of a certain number of variables that we call quantities of interest. So the quantities of interest that we want to track are things like, how much charge do we have in the battery? How much data have we gathered up to now? How much data have we sent to Earth? And what is our distance to the object that we are supposed to be studying? Okay, and the contracts that we write are going to look as follows. So for every one of the modes of operation that we discussed before, remember we had 4 modes of operation, sending data to Earth, charging, changing trajectory, and studying and measuring our object. For every one of those modes of operation, we are going to define a contract for every one of these quantities of interest. So we have two for loops, okay? The first for loop is for every task, and then for every one of these quantities of interest. So the contracts are very simple. This is what we call the atomic contracts, and they are going to look like this. I am trying to point out now to the box labeled A in the slide. So this box labeled A tells us what an atomic contract is in this case study. So it has two input variables. The first input variable is called V initial. So this is the value of the quantity of interest when we begin executing this mode of operation. Delta T represents the duration for which we are going to execute this mode of operation, okay? So this tells us how long we are going to be charging or doing whatever what our task is. And V exit represents the value of the quantity of interest after we are done executing this mode of operation. So, if we are charging, our charge hopefully is going to go from a certain number to something bigger than what we started with after an amount of time delta T. Graphically, the contract can be represented as shown in the diagram in the lower right corner of the slide. So when on the x-axis we have duration, when delta T is equal to 0, okay, just sitting on the y-axis, we have our initial value for the quantity of interest. So this is what the environment is handing to us, you could say, and we are going to make assumptions on that value. For example, if we are doing things like changing our trajectory, we are going to make an assumption on the amount of charge that we have left in the battery, right? Because we need to make use of energy in order to warm up the fuel and then engage our thrusters and so on. When delta T is different from 0, we are going to have a guarantee on the value that our task will hand over to the next task, okay? So when delta T is different from 0, we are going to have a guarantee that is lower and upper bounded by as a relation of the initial value and the duration of the modes of operation, okay? So this allows us to place uncertainty around where we are going to be. Notice that we are using affine bounds for this system, but that of course does not mean that we have linear dynamics or affine dynamics. The dynamics can be as non-linear as they want, as long as they are bounded by this region. So this is what we call the atomic contracts for each quantity of interest for each mode of operation. So the next step that we take is the following. Now, every task that we have in our spacecraft, so remember, every task being charging, changing data with Earth, and so on, is going to have one of these contracts for power, another one for scientific data gathering, another one for closeness to the object that we are supposed to study. And these are the various aspects, the various viewpoints of this particular mode of operation of the spacecraft, okay? Now what we can use is the operation of merging for contracts in order to obtain a contract for the entire task. So this contract, represented by A operation mode and G operation mode, is giving us the information, is giving us everything that we care about regarding the spacecraft operating in a particular operating mode, okay? But I just want to stress that the advantage of having done this in pieces is that we could write contracts that only represented a specific concern of the mission. So only power or only scientific data. So again, we are less prone to make mistakes by doing so. So at this point, we have a contract for the mode of operation. So what happens next is the following. Remember that we wanted to evaluate a sequence of these modes of operation. And at this point, we have been able to compute a contract for each of the modes of operation of the spacecraft. So in order to obtain a contract for the entire mission, which is going to tell us what we can expect our spacecraft to do, for the entire mission, we use contract composition. So we compute the contracts of all these tasks in the sequence. And remember from our discussion of the two interconnected components that the outcome can be of two forms. Either composition works or it doesn't. When composition doesn't work, it means that there is an interconnection problem between two tasks or between the first n tasks and the n+1 task in the system. So what that means is that our spacecraft is not guaranteed to satisfy the assumptions of some internal task that we want to run, okay, under a certain condition. So again, catching that kind of bug, now that we have many tasks in the sequence, could be very, very difficult. But in this case, we are getting it immediately because we are operating directly on specifications. On the other hand, when the result of composition is a contract, we have the 100% certainty that our spacecraft is going to satisfy this specification of the system level composition, provided, of course, that the data that we enter for the specifications of the parts was correct. So at this point, we have a way to evaluate whether a certain spacecraft, okay, is feasible in order to address this particular mission. The next step that we have here is, well, how quickly can we do this kind of analysis? So what I just want to point our attention to this second line, this 20-step line right here. So JPL carried out an experiment in which they tested 200 different spacecraft configurations. And when I say spacecraft configuration, what that means is that each spacecraft has different characteristics for charging, different characteristics for exchanging data with Earth, and so on. Okay, so the contracts are changing for every spacecraft. So they generated 200 spacecraft configurations, and they generated schedules of length 80 and of length 100 tasks. Okay, if we have done planning before, we know that a plan of length 80 is quite considerable for our for planning tools. Right? So in this case, 20 step means 100 tasks. These are some of the numbers obtained from such an approach. So we are doing on the order of 10,000 contract compositions with this many constraints and so on. But the analysis of 200 spacecraft, is done in the order of between 1 and 2 minutes on a modern workstation. So this is encouraging from the perspective that remember that what we wanted to do was to get this shallower feedback loop as compared to what we have today. So it seems that contracts are allowing us to move in this direction of being able to do this efficient analysis in the early stages of the design process. Okay, so in this case study, we saw how to apply these operations of merging and composition to do this system level design. So what I would like to do next is to discuss a different case study that illustrates a different operation on contracts. But so let us now consider a different case study that will illustrate a different operation on contracts. And the situation that we are addressing looks like this. So suppose that we are developing a self-driving car, and our objective, of course, super high level objective is that this car be safe. Okay, and the situation that we are going to be considering regarding the safety of this car is that we want it to act well. Okay, whenever there is a pedestrian on the crosswalk, and I'm going to specify very soon what that means. So most of the components in our car, suppose that we know how to develop, right? But the specification that we really want to nail down is going to be the specification for our perception component of the car. So regarding perception in autonomy, right, what the formal methods community has frequently used is a notion of detection rates for various classes of objects. So what that means is this. What that means is that the specification usually looks as follows. We say, if there is a pedestrian on a picture, in our perception system, how probable is it that my perception system will tell me that there is a pedestrian? Okay, that's what we mean by a detection rate. Of course, we can use also false positives and all of that, but we are going to keep it simple and just talk about this notion of detection rate. However, one difficulty that we usually have with perception is that a priori, it is not so straightforward to know how much is good enough. I mean, do we need a perception component that is like 1 minus epsilon for a tiny epsilon, or is 80% detection rate sufficient for our application? So this is what we are going to try to address here, and this will become more concrete very soon. So in order to address this particular case study, we are going to be using a different operation on contracts. So the operation that we considered for the space mission case study, right, was this notion of composition that said, let me go from an interconnection of of boxes into a box that I place around my entire structure. So I go from the parts to the whole. So what we are going to be using now is the opposite. We are going to be going from the whole to a part in the following way. So let us take a look at the diagram that is on the lower right part of the slide. The outer box here represents a system that we want to build, okay? This system has top level specification AS and GS, which means assumption for my system and guarantee for my system. So this is our objective for what we want our system to do. Now, in addition to having this objective, we also have inside of our system a part that we know for sure that we are going to use. And for that particular component, we have a specification A1, G1, which is the assumption and guarantee for that object. For example, you're making a car and we already decided that there is an engine that we are reusing. Okay. So the question that we ask is, what is the contract that we have to place in this question mark such that the operation of the two elements inside the bigger box concurrently, okay, will satisfy this top level requirement. So that is called a quotient in the theory of contracts. So what we are extracting is going to be this inner box that has inputs O1 and I2 and output Y, okay, that together with A1, G1 will give us the top level specification. So this is the notion of quotient, and just for reference, the operation of quotient in the algebra of contracts is actually optimal in the sense that if there is any specification that does the job for us, meaning any specification that will make the system work, then that is by necessity a refinement of the quotient. So it has that nice optimality property. So let us go back to our perception system and let us see how to apply this. So again, our situation is that we have a car that is approaching this crosswalk, and on the crosswalk we can have a pedestrian, or the crosswalk may be empty, or the crosswalk may have some other object that is not a person. So we are going to understand our car as a system that contains two elements. So there's going to be a perception component that recognizes classes of objects, and there's going to be a controller which actuates the vehicle. Okay, so as we said before, a priori assigning a specification for perception is non-trivial because every number seems like an arbitrary choice. Okay, 70%, 90%, why? Right? So what we are going to do in order to try to generate a specification for our perception component is to use data that we actually have regarding self-driving cars. So certification authorities are going to tell us how many failures are allowed in a vehicle for every million miles or something like that. So what they are going to give us is a sort of probability of failure of our design. In our case, we are going to generate a top level specification for the entire car that says, the probability of being safe. Okay, so we are encoding in some temporal formula what safe means for us. And as you can imagine, for us being safe means, okay, don't be in the same physical location as the pedestrian at the same time and something reasonable like that. So we are saying we are going to place a guarantee on the probability of being safe in a relationship with the visibility in the environment. So visibility means, we can see clearly, right? So we are going to say if the visibility is very high, our probability of being safe is going to be also very high. If the visibility degrades in the environment, we are going to allow our probability of being safe to slightly degrade. Of course, we are going to place an assumption on the visibility in the environment in such a way that if the visibility falls to below a certain threshold, we will be outside scope and we will need to take some sort of emergency action. So for example, our vision system gets completely occluded in the car and so on. So this is our top level specification for the system. This is data, again, that we can get from a certification authority. Regarding the controllers that we use in the system. So the situation that we consider is slightly more complicated in the sense that what we do is that instead of considering a single safety concern, we consider three kinds of safety concerns, okay? So one safety concern is when there's a pedestrian, another one is when the crosswalk is empty, another one is when there is some other object on the crosswalk, but the idea is exactly the same. So for each of these situations that can happen on the crosswalk, we are going to have a different controller that knows how to steer actuate our vehicle. And we can generate specifications for each of those controllers using statistical model checking in the following way. The specifications that we write for the controllers are going to, the specifications that we write for the controllers are going to look as follows. Let us take a look at the one in the top left corner of this system box. So here we are going to make a guarantee on the probability that a certain controller is safe in a relation with the detection rate of the perception component. So detection rate means how likely is it that the perception component is telling me the truth. So if the perception component tells me the truth most of the time, then okay, the controller is going to be required to be extremely safe. If the perception component makes mistakes, then the controller can also make mistakes regarding safety. So we have this graceful degradation. And again, we are going to place an assumption on the detection rate of the component. So the situation in which we are now is as follows. So we have a top-level specification for the system, and we have specifications for each of these controllers that we have inside our system. So the boxes look like this. We can use composition in order to bring the three controllers into a single controller contract, and we can use merging in order to bring the three viewpoints of the system-level specification into a single contract for the entire system. So now our boxes look as what is shown on this diagram on the left-hand side of the slide. So we have a system-level spec, ASGS, and we have a controller specification. And what we want to know is the question mark for the perception component. And we can do that using the operation of quotient of contracts. So using the quotient of contracts, we can compute the specification for the perception component, which is going to look as the diagram shown in the bottom right part of the slide. So this is going to be a contract that makes assumptions on environment visibility and will make a guarantee on the detection rate that this perception component has to offer. And details about the case studies, how we computed everything and so on, can be found on Pacti.org. Same for the space mission case study. Something that I would like to point out regarding where we are now in the design processes is the following. Notice that, imagine that we are the system integrators. We had a specification for the entire car. That's what we wanted to build. We have a specification for a part of the car, and we computed a contract for the perception component. At this point, we, as the system integrators, are free to provide this contract to the perception expert. And we know a priori that if the perception expert implements this contract correctly, our system will work. That's a very nice value to the methodology. Not only that, but notice that the contract that we are providing to the perception expert only has data about the interfaces of the perception component. It only knows about visibility and detection rate. In other words, we, as the system integrators, do not have to reveal to the perception expert anything about what is going on in the rest of the system. So this protects, of course, the system integrator from revealing any sort of trade secrets that may be present in the rest of the system. And it also is helpful for the perception expert because now this person is not overwhelmed by details that are unnecessary to carry out the task of perception. So these are some of the methodological benefits of this, and as I mentioned, this can be found in Pacti.org. Okay, so great. So at this point in our considerations of case studies, we saw how contracts can add a new tool to the kinds of things that we are doing today in system design, and we introduced their contract operations. What the objective next is to say, okay, but what are really the mathematics of these objects? So let us define clearly what is underneath all of this. So the starting point in order to define contracts is the notion of a Boolean algebra of specifications. What do we mean by that? So what we assume that we have to start with as we are doing the system is a language that we use in order to express what matters to us in the system. And we are going to require that language to have Boolean semantics. So by Boolean, what I mean is that every component either has a property or does not have a property. Okay, and that's really, you could say, the core of what it means to be Boolean in this case. And of course, we have the logical connectives, ands and ors and so on. For example, if we are dealing with things like linear temporal logic or signal temporal logic, of metric temporal logic, of all of these, all of them have Boolean semantics. Okay, a component either satisfies a property or it does not satisfy a particular property. So I just want to be clear regarding how we are building this infrastructure. What you have to give to start talking about contracts is, what do I want to say about my system? So what are the variables that I care about? What are the kinds of mathematical statements that I am going to make in my system? So having that on the table, this is how we build the contracts. So, and this is in their we could say formal expression. So the contract algebra is given by this set. So contracts, notice that these are contracts over B. So contracts, if you give me a Boolean algebra B, we are generating an entire contract algebra for that language of specifications. So the contracts over B are going to be the pairs A, G, and A and G are going to be, okay, these are my, A of course is going to be my assumption and the G is going to be my guarantee. And these guys are going to be elements of the Boolean algebra. I'll say what op means in a second. And the constraint that we impose on the pairs A, G is what we have here on the right-hand side. Let me just say, what is the role of the constraint that you see on the right-hand side of this pair? If we had any pair A, G, that's devoid of semantics. Okay, so we would simply be taking assumption, guarantee. Well, but that doesn't mean much yet. What the right-hand side of that expression is giving us is the assume guarantee semantics for the pair. Notice what this is doing. When imagine that A is equal to 0. When A is equal to 0, this constraint is forcing the guarantee to be equal to 1. So, in other words, what we are saying is that if you do not satisfy the assumptions of the contract, then the guarantee of the contract is true by default. In other words, whatever the component does is okay if you do not satisfy its assumptions. Notice that this is equivalent to the legal notion of a contract. If someone does not satisfy the liability, the assumptions of a legal contract, then that person is not responsible for anything in the contract. The contract becomes void. Right? So this is what that constraint there is doing. So contracts have the following notion of order that, as we mentioned before. So we say that a contract A, G is less than a contract A prime G prime when the following happens. So a contract being less than another contract, we tend to think as the contract on the left-hand side as being more refined or more demanding or a harder specification to satisfy. Okay, so we call that order refinement. But so we say that a contract is harder than another contract when something happens. Okay. Either the task that we are asking the harder contract to do is more difficult. That means that the guarantee of the more refined contract is more difficult than the guarantee of the more relaxed contract. And the other way in which a contract can be more difficult than another is when, imagine that the two contracts are asking us to do the exact same thing. But one of the contracts tells me, okay, now you have to do the same thing, but for a much wider set of environments. So we would say that is more difficult, right? I mean, imagine someone tells you, okay, you have to do 100 push-ups at between 20 and 25 degrees C, and somebody tells you have to do the same number of push-ups between 0 and 45 degrees C. So that's clearly much harder. So notice that the order of contracts is covariant in the guarantees and contravariant in the assumptions. By the way, the reason we have this up in the definition of contracts, this C of B right here, is so that the order of contracts is actually directly encoded in this definition. Okay, we don't even have to write this order explicitly, but this is the order of contracts. Okay, so we introduce contracts in this definition C of B. We introduce this notion of order. What I want to say next is to express a very important relationship between binary operations in the theory of contracts. So first, we introduce this notion of the reciprocal of a contract. So if someone gives us a contract A, G, the reciprocal that we represent with this -1 is simply obtained by flipping, okay, the A and the G. So some people in the literature call this mirror because, these kinds of look like looking at your component from the outside, right? You provide guarantees G, the mirror has assumptions G. You assume A, the mirror has guarantees A. And the reason that this reciprocal operation is interesting is because it allows us to relate operations. So we say that two binary operations on contracts, circle and diamonds, are the duals of each other when you can get the reciprocal of one of your operations by applying the other operation to the reciprocals of each of your contracts. So this should remind us of De Morgan's rules, okay, in Boolean algebra, right? So remember that when you have negation of a conjunction, you flip conjunction with disjunction, and it looks exactly like this. So except that this notion of duality is, we are using in order to relate contract operations. So what I find remarkable about the algebra of contracts is that this is all we need in order to derive all the operations that are relevant for system level design. In other words, without introducing any additional axioms, we are going to obtain the entire set of operations on contracts. And we do it like this. So the order that we just discussed on contract operations, of course, is going to introduce a least upper bound and a greatest lower bound. So these are conjunction and disjunction. So we are obtaining these two binary operations, okay, from the notion of order. And it turns out that these two operations happen to be duals of each other, just like they are, in the Boolean algebra. We know what conjunction and disjunction are used for regarding system level design. So conjunction is used when we have two contracts that apply to the same design object. Say, for example, you have a contract that says, this is what my self-driving car has to do at night, and this is what my self-driving car has to do when it is raining. The conjunction is a contract that remembers the two things, what you have to do at night and what you have to do when it is raining. Disjunction is used for product lines. Suppose that we are Toyota and we have several sedan vehicles, and each of them has a contract. Disjunction is the contract that represents the maximum amount of shared functionality between all these cars. So you could say it's like the weakest example of the class. Okay? So disjunction and conjunction come from order, and they are duals of each other. The operation merging that we saw before in the case of the space mission case study can be obtained using the notion of tensor product from commutative algebra. So this is actually quite a recent result. In the past, we didn't understand really what was the algebraic basis of merging, but it is a tensor product. The dual notion of merging is the operation of composition. So remember that composition is used to build systems out of parts. So the operation of merging and composition are these extremely useful binary operations. So what we have here, these four operations in front of us, are what I would consider what I tend to think of them as the constructive operations on contracts. But as we saw before in the example of our autonomous car, right? We not only want to build things. Sometimes we want to extract things. So the notion of quotient of assumed guarantee contracts is obtained by using this notion of right adjoint from category theory. So composition builds things, quotient, kinds of takes things apart. And it turns out that not only composition has an adjoint, but merging also has an adjoint. And adjoints should really be understood as the operations that optimally undo whatever the operations on the left-hand side do. So as we just saw, quotient is the adjoint of composition, separation is the adjoint of merging. What I can only call a miracle, it turns out that separation and quotients are duals of each other as well. Okay, and to make the long story short, turns out that disjunction and conjunction also have adjoints. The adjoints, by another miracle, happen to be duals of each other, and we get this kind of diagram. I just want to state again the fact that this diagram is obtained by pure mathematical and logical exercise, not by the imposition of axioms, right? Which is, as we are building a theory of system level design, I think that this is very refreshing, because it tells us that we are on fairly solid ground that came from all this tradition, of course, of computer science and systems engineering and all that. So it's very beautiful, in my opinion, to see this. So we know how to compute in closed form all these binary operations, and here are briefly their closed forms. And something that I would also like to mention about the algebra of contracts is the following. So one question that was recently addressed was this. The definition of contracts that we introduced a couple of slides ago, said, okay, you give me a Boolean algebra and then you build contracts in this way. But there was one important question that had to be addressed, which was, is this construction of contracts, ad hoc, or is it mathematically canonical in some sense? Okay, is it like the only thing it can possibly be, right? In a precise mathematical sense, it definitely looked like it. It definitely looked like it, because if we consider, this kind of diagram, there is so much unity in this. I mean, this is so compact, right? From the definition, we have all of this. So what we are saying in this slide is that contracts are indeed canonical, and this is and this was shown by using a tool from category theory called adjointness of functors. And the way in which it is shown that contracts are canonical is by showing that contracts are the left adjoint to the closure functor of a class of algebras to Boolean algebras. So what happens in category theory is that the notion of adjunctions of contracts is unique. So, okay, up to unique isomorphism, as they would say, but due to the fact that adjoint functors are unique, what happens is that there are some functors that are super important, right? In category theory. So you can imagine the identity functor is central, right? And there are some others that are central. The closure functor is a very important functor always. So what happens is that if you get to be the adjoint of one of these important functors, it's like you are related to someone very well known, right? So that's what gives this canonicity to the contract algebra, the fact that it is the left adjoint, of this central functor. So this is what we wanted to discuss regarding this mathematical aspects of contracts. Okay, so now we are going to say a couple of things about control and about security. So here we have a recent application of these ideas to layered control systems, and the kind of situation that we wanted to address was the following: is that today in robotics, when we look at quadrupeds and bipedal robots and so on, it is quite common to implement their control system as a layered architecture. So what we have is a layer of planning, then we have a layer of trajectory generation, and then we have a layer of actuation, of low-level actuation. Okay, and what tends to happen, we observe that what tends to happen is that we have very good mathematical tools to analyze all these algorithms in isolation, and then when we go to implement these algorithms in hardware, there are many artifacts introduced by our implementation that are not reflected in our original mathematical analysis that tend to get ignored. So, for example, the relative rates of the clocks that we are using, for low-level actuation and for the trajectory generation, the offsets between those clocks, the jitter in the clocks, and those kinds of things. And so sometimes they get ignored, sometimes leading to failure in the implementation of these devices. So the objective that we set was to say, well, can we write contracts for each of these control layers in such a way that we are going to make assumptions on the timing characteristics of the clocks that we are using to run all these various algorithms, and on the relative delays in between the various blocks, in order to be able to prove the stability of the entire system by only using these contracts in such a way that if our local implementations satisfy these contracts, we are going to get something we are going to get a system that is stable and that we are happy with. So one challenge that needed to be addressed here was the fact that the logical formalisms that are typically used in applications, such as LTL, STL, and a few others, they tend to refer to a single clock in our system, right? So LTL tells us about episodes. Something happens now and now and now and now. STL is continuous, also with a single clock for all the signals that we have in the system. So we wanted, in order to address this, we needed to introduce a logical formalism that would allow us to express predicates according to various clocks that could be present in the system. So the methodology that we wanted to provide was to have contracts expressed using this logic that we ended up calling multi-clock logic, and we were able to write contracts for the various pieces in the system. So contracts for trajectory generation, contracts for low-level control. We were able to prove that the composition of those layers would yield a stable system. And then, in some of the experiments, we would create implementations of each of our contracts and show that when we did not respect those contracts, the system would not satisfy its requirements, and it would satisfy its requirements when the implementations were correct. So I would call this a first exercise, in the direction of applying these techniques for multi-layer control. And of course, one area where will be very nice to bring these kinds of reasoning is for multi-agent systems as well. Right now, when we don't have not only one object, but a collaboration of objects that are carrying out a task. So yeah, this is this recent work on applications of these ideas to control systems. So the next one that I would like to mention is security. So regarding security, we have the following situation. So in cyber-physical systems, of course, we are interested in so many things, right? We are interested in their safety, security, manufacturing, performance, and all sorts of things. But security in general, offers a challenge, which is the following. So assume guarantee contracts, as we are defining them until this point, operate on what the formal methods community would call, trace properties. Okay, so a trace property is one such that for the evaluation of which, for the satisfaction of which, I can go behavior by behavior in the property and say, yeah, my component satisfies this behavior, my component satisfies this behavior, and so on. And there exist many security properties that can be expressed using trace properties. So, for example, if we say something like, no execution of my system should be able to access some highly privileged area of memory, the way to do that, right, will be to prove that our piece of software, is never trying to make access to that particular memory location. And we could do this by running all executions and checking that we are never, touching that memory location. So this will be a security attribute of our system that is a trace property. But there exist some attributes that are important for security that are outside the scope for the scope of trace properties. So one of them, for example, is called observational determinism. So the idea with observational determinism is that, we want to say this. You want to say, suppose that I execute my system twice with the exact same inputs. I want to make sure that my outputs are the same, or that the timing internally is the same. Okay, whatever is observable is the same in the two different executions of the system. And this is important for those kinds of timing attacks, that we have sometimes seen to hardware, right? In which by the difference in execution time, you can infer whether there's a secret and so on. But the key in what we just said right now is that for two different executions of the system, the output is, the observable is the same if my inputs are the same, okay? So now we are predicating on multiple executions at once. That is not a trace property. That is called a hyper property. Another example where that is important is in when we are trying to build robust classifiers. So, the situation with adversarial examples, of course, is, you take an example, you modify it a bit, and you get something else, some other class in your classifier. So by robustness of classifier, what we are saying is that, okay, if I bring one input and another input that is slightly perturbed, okay, my output is similar in my classifier. So this is also something that brings us to this world of hyper properties. So now the question becomes, look, there are some system attributes that are clearly outside what we can express using trace properties or Boolean algebras, which are largely equivalent. So the question is, can we do, what do we do, regarding these attributes of systems that cannot be expressed using trace properties and that need this more expressive power of hyper properties? So there is a theory that we call hyper contracts, which provide assumed guarantee reasoning for attributes of systems that are expressed using hyper properties. Okay. And then, I will briefly discuss this. So this notion of hyper contracts is built in stages. First we have this something that we call the theory of components, which are the elements on which we are making predicates. Then we have something called a theory of comsets, which are the system attributes that we want to check for our components and systems. And the hyper contracts are pairs of those system attributes. And we have had some of the examples up to this point. They have been pencil and paper examples done regarding hyper contracts are to security applications in which we want. Okay, in the first case, what we want to check is that a secure input is not able to be revealed into a public output, and then we use the notion of a completion of a system using a quotient for hypercontracts in order to design a system that is provably secure according to this. And regarding robustness, okay, we have applications to self-driving cars in order to compute the specification of the robustness in a certain car that will make sure that the entire system is robust against certain adversarial examples. So that is our discussion on hypercontracts. And now, as to wrap up, I would like to say a couple of things about contracts in general. So what is the summary of what we have discussed so far? First of all, what do we gain, right? By using contracts. So one thing is that we think about systems and subsystems in terms of their specifications, not their implementation details. So the benefit is that conclusions will hold for any implementation that adheres to the specification, right? Something else that we have noticed as a benefit from using them is that contracts make assumptions, first-class elements in the theory. We have to always specify explicitly the assumptions of the components. And from our experience, operating on assumptions is considerably less intuitive than operating on guarantees. Let me give you an example. Sometimes, we have presented examples that are similar to our circuit example using the quotient. The quotient has the quotient, even in the simplest examples, are actually extremely unintuitive to compute, because one has to be very careful about the assumptions of the resulting element. So yeah, this has reinforced our notion that assumptions are considerably less intuitive than guarantees. We have seen, particularly from the benchmarks run by JPL, that contracts allow us to scale compositional reasoning to large designs. And we saw how the algebra has many operations that are relevant for the design process. And the last point that I would like to make here is that, what is it that contracts bring and what is it that they don't? So to a certain extent, contracts are not here to replace anything. So contracts provide us the mechanism to understand the interconnection of components as we are building systems. But when it comes the time to prove that a certain component has a certain stability property or thermodynamical property or you name it, kind of property, we are going to be using the tools that are appropriate for that particular area of design. So what we are doing with contracts is completely complementary to what already exists and does not replace, but we could say adds a new kinds of analysis to it. So what we have discussed right now, has been collaboration with a wonderful group of people, and I'm of course grateful to the various agencies that have funded our work through the years. And that being said, I'd like to thank you very much for your attention and happy to address any comments or questions.